Hello everyone. In this video, I'm going to talk about the common roadmap used in discretizing partial differential equations using finite difference formulation. Assume that we have a partial differential equation of a scalar u. It is typically formed with the time derivative of u, a linear operation on u, and a source term q on the right-hand side of the equation. First of all, as a very common procedure in the mesh-based numerical formulations, we usually discretize this partial differential equation in space using a numerical discretization technique. For example, we could use finite difference method, finite element, finite volume, or high-order global methods. In this series of videos, we only talk about the finite difference method. Through the spatial discretization, we could evaluate our application of numerical formulations with field matrices. For example, we could know the associated truncation error of this numerical discretization. We could also check the consistency and order of accuracy of the spatial discretization as well. After the spatial discretization, we need to check if the time derivatives are involved in the governing equation. If it is not, we have a steady or equilibrium problem. Following this path, we arrive at an algebraic equation system, the so-called finite difference equations. After imposing appropriate boundary conditions, we can solve these finite difference equations using linear algebra for the numerical solution. On the other hand, if we have a transient problem with time derivatives, following this path, we arrive at a set of ordinary partial differential equations. In the ordinary partial differential equation, we only have derivative with respect to time. The other algebraic terms, for example, the characteristic matrix A and the source term F, are both resulted from the spatial discretization. In computational physics, we call this ordinary differential equation as a semi-discrete form, in which the spatial derivatives are discretized by spatial discretization schemes, and the temporal derivatives remain to be analytical. In the temporal discretization, we could also obtain the order of accuracy of the temporal discretization. After the application of temporal discretization, we finally have a set of finite difference equations for the original partial differential equation. To solve these finite difference equations for transient problem, we need to impose both the boundary conditions and the initial conditions to obtain the numerical solution using linear algebra. In temporal discretization, we are particularly concerned with the stability of the applied temporal schemes. The stability of the temporal discretization scheme is usually checked with the exact solution to this ordinary differential equation. It should be noticed that this is the exact solution to the ordinary differential equation instead of the governing equation. We will talk about the techniques to investigate the stability of different temporal discretization schemes in the following videos of this series. In any numerical formulations, the key concern in the numerical solution is if this numerical solution will converge to the exact solution to the original governing equation. However, the exact solution to the original governing equation is usually difficult to find. Otherwise, we won't take a numerical approach to approximate the governing equation, despite the convergence property is so important in numerical formulations. So there must be a way to circumvent this hurdle. To this end, the stability check is usually done to indicate the convergence property by Lexus equilibrium theorem. The Lexus equilibrium theorem stated that for a linear well-posed initial value problem, a consistent finite difference approximation is convergent if and only if it is stable. Hence, there are few concepts we should be clear. To evaluate the convergence property of the numerical discretization, we take the limit of the difference between the exact solution to the governing equation and the numerical solution of differential equation as the mesh size and the time step are refined toward zero. When we talk about the stability of a numerical discretization, we mean that the numerical solution of the finite difference solution remain bounded as the dynamics of the equation march in time. In the following video of this series, I'm going to elaborate more details on the algorithm used to check the stability of different families of temporal discretization schemes. Here, we also need to pay attention to the well-posedness of the problem, which means that the solution must exist and unique. We also need to make sure that the solution's dynamic evolve continuously with the initial value in time. In the concept of consistency, we need to make sure that the truncation errors resulted from the numerical discretization will also approach to zero as we refine the mesh until approximately zero. Here, the truncation error is defined as the difference between the exact solution to the partial differential equation and the numerical solution to the finite difference equation. In finite difference method, we approximate the numerical solution on a mesh grid with Taylor series expansion with respect to its neighbors. Hence, the truncation arrow exactly tells us that the maximum possible errors based on your truncation of terms in Taylor series expansion. Frequently, we are required to know the order of accuracy of the applied numerical discretization schemes. It is extremely important number to guarantee the reliability and the accuracy of your numerical solutions. In a nutshell, the order of accuracy P of a numerical discretization in finite difference method is the power of the leading term after the truncation in Taylor series expansion. I'm going to give more intuitive elaboration in the following videos. In the following videos, I'm going to talk about the detailed algorithm of different spatial and temporal discretization schemes and their stability characteristics. I'll give a lot of examples to elaborate how it could be applied to some sample cases. In particular, I'm also going to demonstrate two numerical techniques to investigate the stability of different families of temporal discretization schemes. Thanks for watching.